Okay. Section 2.2 is going to explicitly say kind of what we were hinting around at the previous section, and that is the limit of a function and the limit laws. And we're going to get a list of laws at the end. So the first thing we want to look at here is this graph of this function. Here's a rational function that is undefined at x equals negative 1. I'm sorry, at x equals positive 1. You can tell this function is undefined because there's a hole in the graph, right? And you remember from algebra that x squared minus 1 factors into x plus 1 times x minus 1, correct? And if you divide this by the factor x minus 1, these common factors are going to cancel out, and what we're left with as an equivalent function is a new function, g of x, that's equal to x plus 1. Well, there's a linear function where the y-intercept is 1, the slope is 1, and it's just undefined right here at this point that factors out. But if we were looking at the limit as x gets closer and closer to 1, here we're approaching from the left and then again from the right. As x gets closer and closer to 1 from both the left and the right, the y value of this function is getting closer and closer to what? To 2. And if you plugged a 1 in here into this function that's similar to or algebraically similar to the function that we started with, if you looked at g of 1 right here, we end up with 1 plus 1 is 2. So algebraically, the limit as x approaches this 1 is going to be equal to 2, and also by looking at the graph. As x gets closer and closer to 1, the y value here is getting closer and closer to 2. Does that make sense? That's what a limit is, essentially. Okay? So you can algebraically manipulate this function so that you end up with a similar function, we're going to call it g, where g of x is almost the same as f of x, except where f of x is undefined. Okay?
This is only for graphs with an open circle?
Yes, only, and you only have the open circle if you have a common factor that will reduce between the numerator and denominator of a rational function.
Could you redefine the difference between f of x and g of x?
F of x and g of x are the same function, except where the original function right here is undefined. That function is undefined because when x is equal to 1, you have a 0 in the denominator of the function, and thou shalt not divide by 0. First commandment of mathematics. So f and g are exactly the same everywhere except at that one point. Okay? That's what these symbols mean. Just saying it with symbols instead of words. They're the same function everywhere except for that one point where the original function is undefined, because that's where the denominator is 0. Okay? I hope I answered your question completely. If I don't answer your questions to where you understand it, don't let me get away from the question, because when you go back and view the video, you won't have an answer that you understand there either. Okay? So, I lecture very conscious of what's going on with the video and what you guys are going to be able to access later. Okay. So, what we see from this problem is that a function doesn't have to be defined at a point. In order for a limit to exist. And that's an important thing to note. Now, this function is not continuous at that point. There's a hole in the graph at that point. And I think sometimes we get confused about continuity and limits existing, because we're going to get into continuity in a later section. There's a hole in this graph, but the limit still exists. Any questions? All right. So here's another function, y equals x plus 1. And if I want to look at the limit, once again, as we get closer and closer to 1 right here, from the left and from the right, what I see is that limit is still the same right here. We'd say that the limit as x approaches 1 is 2. Here the function's defined at the point, and that's all fine, well, and good, but it doesn't have to be defined at a point. Remember, there's this mark right here is not here. Okay? And this leads us then to the informal definition of a limit. And sometimes I think the informal definitions are easier to understand. Okay, if f of x, the y values, becomes arbitrarily close to a real number L, as x approaches a constant C from either side, meaning the left or the right, then the limit of f of x as x approaches C is L. Okay? In this problem up here, C would be 1. That's the constant that we let x get closer and closer to. The y value that our limit is approaching is 2. As we approach, as x gets closer and closer, gosh, I wish I had 2 pens. As x gets closer and closer to 1 here, the y's are zooming in on 2. So 2, we say, would be our limit there. That's the informal definition of a limit. Now, there's a couple of problems that make this an informal definition. First of all, what does this mean, arbitrarily close? Well, it depends. Are we talking nuclear warheads or molecular physics? You know, I mean, close can be one thing in one set of situations or another. Arbitrarily close is a problem for us, and that's what keeps this in the informal definition limit. In the formal definition of a limit, we're going to be looking at how to determine how close is close. And I believe that's in the next section. Yeah. So, moving on. So here's 3 problems. Okay? Let me see if I can scooch this over some. The limits of f, g, and h all equal 2 as x approaches 1. However, only h has the same function value as the limit at x equals 1. Here, the x minus 1 is going to be a common factor that cancels out. This is the problem that we looked at before. We have a function that has a hole, and the limit is equal to 2. Here we have a function that's piecewise defined, meaning we have our function f, but we fill in the hole right there at x equals 1. So if I looked at g of 1, let me look at this. F of 1 is undefined. Here, g of 1 is equal to, and the limit is equal to 2. G of 1 is 1, but the limit is 2. In the last example here, see, h of x equals x plus 1. The limit is 2, and h of 1 is also equal to the limit. What I want to point out here is that in this situation, we can use direct substitution in order to determine the limit by plugging in the value that we're approaching. That only happens when we have a continuous, well-defined, well-behaved function. Okay? It's the exception more than the rule, by the way. The function does not have to be defined at the limit. It could have a different value at the limit, or it could be equal to, the function could be equal to the limit when you plug in that number for x, a given number for x. It doesn't have to happen that way, though.
So a limit illustrated is just this built-in circle?
Now, a limit is the value that y approaches. Let me pull back up the informal definition of a limit so we can probably see it right here. It says the f of x is the y value, right? So this says that the y value is getting close to some real number. In this case, it's 2. All right? So if the y value gets close to a real number, that real number is our limit. As x gets closer to some number, in this case it was 1. So as the x get closer and closer to 1 down here, the y's are getting closer and closer to 2. A limit is just the value that the function approaches. It's just a happy coincidence that on this last one the function was actually equal to that limit at that point. It doesn't have to be equal to the limit. Okay? This is where I first started struggling in calculus. I can remember Wayne Duncan teaching me. He's a teacher here. He taught me calculus, and when he first introduced the concept of a limit, I'm like, whoa, wait a minute. My head started spinning. But eventually it settles down and it starts sinking in. You just got to not give up on the concept. So the limit is the y value, the f of x, that this function approaches as x gets closer and closer to 1. So what's happening down here? No, it's whatever that constant is.
So we can make the constant 0?
You can make the constant 0, you can make the constant. The only reason they picked 1 here is because how they defined this function. It was undefined at 1, at x equals 1, and this one had a different value at x equals 1. This is going to change. The limits are going to change as the functions change, and it's just been a happy coincidence we've used the same functions. Yes, sir?
So is the limit basically just what y would equal when x is plugged in?
If it were defined there, yes. That's one way to think about it. But see, right here, if x is plugged into this piecewise defined function, you get a different y value out. If x is equal to 1, y is equal to 1, so we have a point. So you can't say that here. That's why we use this concept of getting closer or approaching from the left and from the right. So as x gets closer and closer to 1 from the left, the y value is getting closer and closer to 2 from the left. As x gets closer and closer to 1, I'm sorry, I started with my y's. As x gets closer and closer to 1 from the right, the y value is getting closer and closer to 2 from the right. Does that make sense? So we would say then that this value right here is the limit. Okay? But g of 1 is equal to 1 based on this piecewise defined function. The limit and the function evaluated at this point don't have to be the same. They don't even have to be defined. But they could be defined and they could be the same. Let's move on to another problem, and if we're still struggling, then we'll come back to this some more.
Can you just one last time say what the difference is between the open circle and the closed circle?
Okay. The open circle is a point where the graph is undefined. So right here we say f of 1 is undefined, because if you go to this function f right here and you plug in a 1 in place of x, you end up with 0 over 0, and that's undefined. So there's a hole in the graph right there. All right, but if we plug in 0.99999, we get 1.99999. If we plug in 1.00001, we get 2.00001. All right, using this function. So the limit exists. The limit is 2, but the function at that point is undefined. And here, the limit exists. The limit is 2, because as we approach x from the left and the right, we get the same y values. We're getting close to the same y values. This is that arbitrarily close thing. Here it's f of 1 is undefined. Here g of 1 is equal to a different value, but as we approach from the left and the right, we're approaching the same values of y. And over here, h of 1, the limit is equal to 2, but h of 1 is also 2. It doesn't, I guess my point is, it doesn't matter what's happening to the function at a point in order for the limit to exist. As long as the y values are approaching the same value as x, as you approach x from the left and the right, as long as the y values are the same, the limit is going to exist. Does that help clear things up? Okay. Sorry. Moving on then. We'll see if it makes sense in just a minute here. All right, number 2. For the function f of t graphed here, find the following limits or explain why they do not exist. The first thing we're going to look at is the limit. By the way, this is limit notation. This is read the limit as t approaches negative 2 of f of t. Let me translate that for you. The limit as t approaches negative 2 of f of t is, and then we've got to look at the graph. As we approach negative 2 from the left, what is the function approaching? 0. As we approach negative 2 from the right, what is the function approaching? 0. So we would say then that this limit exists and the limit is 0. Does that make sense by looking at the graph and based on what you understand the limit to be? Any questions? Do you get it? Because if you don't, I'll explain it again. You don't get it. Okay. Going back to the informal definition of a limit, I'm going to pull up that definition just for a second right here. It says, if the y's get really, really close to a real number, as x approaches some constant from both sides or either side, then the limit as x approaches that constant is some number L. So when we looked at this graph right here, this means the limit of as t approaches negative 2 of f of t. There's your function. So the function, the y values are getting really, really close to this point 0. The ordered pairs for this point right here is negative 2, 0. Do you agree that that's what this point right here is? This function's undefined there. How do I know that the function's undefined right here? Because it has an open circle. The function's not defined right here, but as x gets closer and closer to negative 2, the function's getting closer to 0. As x gets closer and closer to negative 2 from the right, the function's getting closer and closer to 0, the y value right here at that point. Does that make more sense now? Okay. Unfortunately, on the video, you're not going to see my fingers pointing, but I was pointing like right here. As we get closer to x from the left, the graph is getting closer and closer to a y value of 0. As x gets closer and closer to -2 from the right, the y value of the function is getting closer and closer to 0. So we would say then that that limit is 0. Yes, the limit is the y value. This number down here is what x is approaching. We're looking for the y's, the function value. The limit is the y value.
The limit will never be x.
No, x is what we're approaching. The limit is the value of y. That's a good point to make. It never dawned on me to ask that one. This is why I like recording live classes as opposed to just recording lectures. Okay, and part B, what is it that we're asked to find? Can you interpret these symbols in your head? We're asked to find the y value of what? Of the function when x is -1. Well, looking at that then, can you tell me what this might be? Does everybody see why it's -1? As x gets closer and closer to -1, the y value is approaching -1 from the left and from the right. Correct? How about right here, the limit as t approaches 0 of f of t? Does not exist. Now, why would I say that it does not exist? As we approach from the left, we get -1, and as we approach from the right, we get +1. And you'll see that in a minute when it comes back up. So here we're approaching from the left, we get -1, and as we approach from the right, we get +1. Since that left-hand side and the right-hand side are not the same, we say the limit does not exist. Is f of 0 defined?
Yeah.
Yes, it is. It's 0. Now, I just asked a different question. It wasn't about a limit. The question was, is f of 0 defined? F of 0 is equal to 0, because there's that point right there. The limit doesn't exist because as we approach from the left-hand side, we get a -1. Now, I'm going to spill the beans here. We have things called one-sided limits. The limit as t approaches 0 from the left of f of t is -1, and the limit as t approaches 0 from the right is +1, and if the left-hand limit and the right-hand limit are not the same, the limit does not exist. I've spilled the beans about something that I haven't told you about yet, but that's what that informal definition meant. It has to approach the same value from either side, either the left or the right. So here our left-hand limit and our right-hand limit are not the same. Any questions? Make sense? See, in order to remember, the limit is a y value, right? We get two different y values right here. We're depending on if we come in from the left or from the right. And since it can only be a real number, there's two real numbers. How would you pick? Right? So since we can't pick, we just say the limit doesn't exist. Makes more sense now? Good. I think I'm doing a better job in summer school then. All right, part D. The limit as t approaches -0.5. -1. Because -0.5 is actually about right there. And guess what? The function is defined at that point, and we end up with -1. Because as we approach from the left and from the right, we get the same thing. Okay? Make sense? You sure? Any questions? Do I need to explain anything again, either A, B, C, or D? Moving on. Okay. There are three behaviors that cause a limit not to exist. Three behaviors that cause a limit not to exist. The first one is the behavior differs from the left and the right. That was like the previous problem where we had f of 0. Okay? The limit as t approached 0 was undefined because as we approach from the left we got -1, if we approach from the right we get +1. So the second condition then is unbounded behavior. Because remember, on our informal definition of a limit, we said that it has to be a real number. Well, if the left and the right-hand side are going off to infinity, then infinity is not a real number. So, for example, if I have a situation like this, we would say then that the limit as x approaches 0 of f of x does not exist because of unbounded behavior. And then the last thing that would cause a limit not to exist is oscillating behavior. And an example of that would be f of x equals sine of 1 over x. And I think that's what this is a graph of. If you graph this on your calculator, you'll see the function just start bouncing wildly back and forth as x gets closer and closer to 0. Okay? So here's an example where our left-hand limit is not equal to the right-hand limit. That's condition number 1. Here's a condition where we have unbounded behavior as x approaches 0. None of these functions have limits as x approaches 0. And here, this is a piecewise function, and we have this oscillating behavior going on close into 0. Okay? We know sine bounces back and forth between 1 and -1. But as x gets closer and closer to 0, that argument becomes undefined. The angle becomes undefined. Okay? Any questions? Okay. Theorem 1 are the limit laws. If L, M, C, and K are real numbers, and if the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to M, then we have the following rules. The sum rules. Notice on both of these, what x is approaching is the same. Okay? So, if we look at the limit of the sum of two functions, we can add the two limits together as long as x is approaching the same thing. So, if we add the functions together, we can end up adding the limits together. Does that make sense? If we subtract the functions, we can subtract the limits. If we multiply a function by a constant multiple, multiply that limit. Right here, we were told the limit was L. Multiply that limit by the same constant. And then we also have products, quotients, and power rules, and a root rule. As you work with these rules, you will become more familiar with them. Okay? So here's some problems. Number 54. Notice right here, x is approaching the same thing. So we're told that the limit as x approaches f of x, the limit as x approaches 4 of f of x is 0, and the limit as x approaches 4 of g of x is negative 3. We want to find the following limits. How would I find the limit of g of x plus 3 as x approaches 4? Did we have a constant? The limit of a constant is that constant, and that's not on there. But this is going to end up being, what was the limit as x approached 4 of g of x? Yeah. Let me move this down. So on A we have the limit as x approaches 4 of g of x plus u, the limit as x approaches 4 of a constant 3. Well, this limit was negative 3, and the limit of a constant is that constant, so this whole thing ends up being what? Any questions?
Where you get the negative 3 from?
Where am I getting the negative 3 from? We were told right here that the limit as x approached 4 of g of x was negative 3.
Why'd you write out limit as x approaches 4 of 3 at the end?
Well, essentially what's happening with the sum rule, if you notice, we can distribute a limit across addition or subtraction. That's essentially what's happening, right? If you have the sum or the difference of functions, this is just a constant function, 3. So this is another way you can think about this. It's going to be this limit plus 3. I could have written this just like this, plus 3, because the limit of a constant is that constant. Does that make sense? If it makes more sense like this, I'm happy leaving it like that. But that doesn't help us with this one. What about the limit as x approaches 4 of x times f of x? If you look back up here at the product rule, you can multiply the limits together, right? So another way of thinking about this is, let me write it like this. The limit, I meant to use the thinner pen, hang on. The limit as x approaches 4 of x times the limit as x approaches 4 of f of x. So this is going to be, what's the limit as x approaches 4 of x? Times, and the whole thing is, do you see why this one was 0 right here? You didn't see why? The limit of x as x goes to 4, you can use direct substitution. That's a constant function, right? The only time you can't plug in this number into the function is if that function is undefined. Let me go back to this example. We like the direct substitution if we can use it. See, this function was undefined at the point 1, so I couldn't use direct substitution. This function had a different value at that point, but the limit of x is not undefined anywhere, so I can plug in that 4. It makes sense, I think, looking at the graph, and I want to convince you that it's the same thing, so hang on just a second. So, what we have is, let's look at this. Here's a graph, y equals x. Blue. Okay, we're going to pretend this is a straight line. Sorry. Okay, this is a graph of y equals x. And as x approaches 4 from the left, what do we get at this point right here? 4, y equals x, right? They're the same.
How do we know it's y equals x again? We just assume that?
It's given. It was x times f of x. I don't know the function f of x, but I know what the graph of x looks like.
So that's the function right there.
Yeah. See, this is another one function times another function. I had to just look at this and figure out that the limit as x approached 4 of x was going to be 4. These, the limit as x approaches 4 of f of x and g of x, I know values 4 because they were given. This one I had to figure out. It wasn't given.
And why is the other value 0?
Because we were told so in the problem. You've got to, why do I know that? I don't know why I know that. They just told me that's what it was and I believe them. Because that's the problem. Okay? But this one I had to figure out. This one, I was told up here that limit is 0. That was given in the problem. Okay? All right, let's look at another one. This one deals with the power rule. Part C. We have the limit as x approaches 4 of g of x squared. I had one too many parentheses there. I believe, yeah. Well, what's the limit as x approaches 4 of g of x? And when I square negative 3, what do I get? 9. So this is going to be negative 3 squared. How do I know that? Well, that's what this power rule right here says. The limit as x approaches c of a function raised to a power is just going to be the limit raised to that power. So this is going to be negative 3 squared, which we know is 9. All right? Any questions? Part D. I'm going to get more room here. The limit as x approaches 4 of g of x over f of x minus 1. What is g of x? The limit as x approaches 4 of g of x. So this is going to be negative 3 over, what's just the limit as x approaches 4 of f of x? 0. And then here's a constant, minus 1. So what does this end up being? See how it works? Making more sense? You will have questions about limits asked in this same way on your test. I'm telling you now, put a star by these problems because this is a good way for me to check your understanding of limits. So know how to do these types of problems where I give you values for the limits and then I ask questions like this, asking you to evaluate.
Do we have to memorize that chart, or will we?
That chart will become intuitive as you look at it. It really does make sense. Hang on, I'm going to put a star. Okay. If you add functions together, then you can add the limits together. If you subtract the function, subtract the limits. If you have a constant times a function, it's a constant. I mean, these are going to become intuitive, I think. I don't think you're going to have great anxiety over memorizing this. Okay? But the short answer is yes. You either memorize it or you just know it. But that's why I assign all that homework, is to help you memorize the things that we use a lot. We use this a lot. Okay? Next, we have the limit as x approaches 2 of negative x squared plus 5x minus 2. What do you know about this function? Well, no, just this function right here. If we had f of x equals negative x squared plus 5x minus 2, what shape does it have? Is it going to open up or down? Is it continuous everywhere? Yeah, it's continuous everywhere. It's a parabola that opens down. So isn't it defined everywhere? It's defined everywhere. That means it's a well-behaved function. Polynomial functions are well-behaved functions, and anytime we have a well-behaved function, we can use direct substitution in order to evaluate the limit, because the value of the function at a point will be equal to the limit at a point. So when you are presented with this problem and asked to find the limit, if you notice this information, that it's a well-behaved function, that's continuous, it's a polynomial, to evaluate this limit, all you have to do is look at the opposite of 2 squared plus 5 times 2 minus 2. We can solve this using direct substitution. Okay? We like polynomial functions for this reason. So this is going to be negative 4 minus 2 is negative 6 plus 10 is 4, right? No. Because, yeah. Right there, x is approaching 2. So that's negative 4 plus 10 minus 2, that's negative 6, and 10 is 4. The notes are wrong online. Look at these. It's 4. Yeah. Any questions? The question did get asked, how did I know to plug in a 2 right here? And the answer was, because that's what x was approaching. That leads us to the following theorem. The limit of a polynomial, and a polynomial is where you have a constant times x raised to an integer power plus another constant times x raised to a decreased power all the way down to your constant term. That limit is going to be equal to the polynomial evaluated at whatever point this x is approaching.
So that's what we just did.
It's called direct substitution. Direct substitution just means plug in the number that x is approaching into the polynomial in place of x. Okay? Now, actually, it doesn't have to be just a polynomial function. As long as your function is defined at that point, you can use direct substitution. Okay? Let's look at the following. This is number 18 out of your book. This says the limit as y approaches 2 of this rational function. This is a polynomial over a polynomial. It happens to be a linear over a quadratic. Is this function going to be defined at y equals 2? What do you check for when I ask you, is this function defined at y equals 2? If there's a 0 in the bottom, it's not defined. When y is equal to 2, am I going to have a 0 in the denominator? No, because these are all positive values. 2 is positive. I don't have any negatives there. And no, it's going to be defined. It's not going to be 0. Because this is not undefined at y equals 2, we can use direct substitution. So this is going to be 2 plus 2 over 2 squared plus 5 times 2 plus 6. And that's equal to 4 over what? 4, 10, 20. So that limit is actually 4 over 20, which reduces to 1/5. Go with the 1/5, not the 4 over 20. Okay? Reduce your fractions whenever possible. Any questions? Okay.
Basically, you just plug in the limit.
As long as the denominator is not undefined, as long as the function is defined. I'm going to call it the argument of the limit is defined at x equals c, or in this case y equals 2, then you can use direct substitution. To evaluate the limits. Direct substitution is the easiest way to evaluate a limit. So check for that first. The only time you have to worry is if you have a 0 in the denominator or a negative under a radical. So the only two ways are a negative and a natural log. You know your functions and what makes them undefined. Okay, number 50, we have the limit as x approaches 0 of the square root of 7 plus secant squared x. Can we use direct substitution here? Well, as long as that's not 0, I think we can. Okay, this is where the trig has to come back to you. All right, secant is the reciprocal of which trig function? Cosine. S's and C's go together. Sine and cosecant are reciprocals. Secant and cosine are reciprocals. Y'all remember that? No. Okay, trig is really going to have to come back. Secant x is equal to 1 over cosine x. Right? And cosine of 0 is what? 1. So we can use direct substitution because what this is going to end up being is the square root of 7 plus secant, which is 1 over cosine 0 squared. So this ends up being the square root of what? 7 plus 1, which is the square root of 8, which is equal to 2 square roots of 2. Simplify that as well. Simplify your radical whenever possible. Okay? Sorry, I have kids that are out of school and they keep calling me. All right. Is everybody okay with simplifying the radical? Do I need to review that? Review it once? Okay. All right. It's okay. I'll go over the rules. It takes me less time to explain it than it does for you to struggle with it. All right. Just a quick review. If you have the square root of a times b, that's equivalent to the square root of a times the square root of b, right? What that means is the square root of 8, I could rewrite as the square root of 4 times the square root of 2, because 8 is 4 times 2. And the square root of 4 is 2. And the square root of 2 won't simplify. So if you have any factors of a number underneath here that are perfect squares, you pull out the square root of that factor. And any other factors leave underneath the radical. So the square root of 12 would be what? 2 square root of 3. The square root of 27 would be 9 times 3 is 27. 3 square roots of 3. All right. Square root of 75. 25 times 3. 5 square roots of 3. Okay, good deal. I know it's easier to see when you write it out. Square root of 75, that's the square root of 25 times the square root of 3, because 25 times, yeah, okay. Okay, there's fortunately not a whole lot of that in here, but there is some. All right, limits of rational functions. If p of x and q of x are polynomials and the denominator is not equal to 0 at this point that x is approaching, which is essentially what I just told you. If you have a rational function and the denominator is not going to be 0 when you use direct substitution, then you can use direct substitution on a rational function. So you can use direct substitution as long as the argument of the limit is defined. That means that you can't have a 0 in the denominator. If you do have a 0 in the denominator, you've got to try different things. So, for example, suppose we have this problem right here, and we're asked to find the limit. I didn't write down the problem, so I apologize. Find the limit as x approaches 1 of x squared plus x minus 2 over x squared minus x. What can I do with this? If I plug in a 1, isn't this thing undefined? That means I can't use direct substitution, because if I plug in a 1 right here, I end up with 1 minus 1 is 0. So I've got to try something else. Whenever you have a rational function, try factoring the numerator and denominator and see if you have any common factors that'll cancel out. And in this case, I believe we do. So let's factor. All right, that numerator factors into x plus 2 times x minus 1 over, and out of the denominator I have a common factor of x times x minus 1. Right? Right. Anything going to cancel? Yes, the x minus 1's cancel. So what that means is this function is equivalent to the limit as x approaches 1 of x plus 2 over x. Well, now I can use direct substitution, right? Because it's no longer, the denominator is no longer 0. And remember we said that this function and this function are going to be exactly the same everywhere except at that one point where x is equal to 1. So now I can plug in the 1 and I have a function that's defined there, and we end up with what? So that's 1 plus 2 is 3 over 1. This is 3. Okay? Part B. We have this function which is equivalent to this function. That's just a graph of the same function, only this one's defined at x equals 1. Okay? All right, number 34. We have the limit as v approaches 2 of v cubed minus 8 over v to the 4th minus 16. When we plug in a 2 here, 2 to the 4th is, and 16 minus 16 is 0. That means that we should try to factor, right? The numerator here is going to be the difference of 2 cubes. Do you remember how to factor the difference of 2 cubes? Recall, if you have a cubed minus b cubed, that's going to be equal to a squared plus ab plus b squared times a minus b. I need to move this over some. You probably saw it written with the a minus b first. Any questions? In your calculus book at the front are some basic algebra formulas about this factoring. Yeah. Towards the bottom of the page, I'm looking on the front flap jacket here, there's reviews some factoring formulas. Okay. I'm sure you've seen them at some point in your life, but if you forget, there they are. Look them up. Once again, once you get back into the habit of doing math again regularly, these will stay kind of in the forefront of your brain, hopefully. All right, so this is going to be equivalent to the limit as v approaches 2 of, this is going to be v minus 2 times v squared minus 2v, no, not minus, plus 2v plus 4 over v squared plus 4 times v squared minus 4. Do I have anything in common? Do I have any that'll cancel? No. Do I have anything that I can factor further? Yes. This is the difference of two squares, which will factor further and then cancel with one of these factors here. So this is going to be the limit as v approaches 2 of v minus 2 times v squared plus 2v plus 4 over the sum of two squares will not factor, but the difference of two squares will. And now we have two factors that will cancel. And we can use direct substitution directly. So this is the limit as v approaches 2 of v squared plus 2v plus 4 over v squared plus 4 times v plus 2. By using direct substitution, we end up with 2 squared plus 2 times 2 plus 4 over 2 squared plus 4 times 2 plus 2. Do you see what just happened now? And this ends up being, let's see, that's 4 plus 4 is 8 plus 4 again is 12 over, that's 2 squared is 4 plus 4 is 8 times 4 is 32. 12 over 32 reduces to 3 over what? No. Yeah, 3 over 8. 3/8. Okay?
This is just to find the limit.
Yeah. That is the limit. That was the whole point right here, was find the limit, evaluate this limit. Your answer is, that seems like a lot of work for just a lousy 3/8, right? Yeah, but this is laying the foundation behind the concepts of calculus. Limits, learning about limits is kind of learning about how the engine works before you learn to drive a car. I can drive a car without knowing how the engine works, but it's helpful if something breaks down along the way. I'm teaching you how to work on the engine right now. And y'all are wanting to drive. Just be patient. Okay? I like car analogies. My dad actually made me learn how to change a fuel filter, a tire, and the oil before I could ever drive a car, because those are things he wanted me to know how to do. Do I do that today? No. It's what husbands are for. I just drive the car. Okay? All right. Here's another problem. It's a rational problem. It's got a square root in it, so ick, but we're not going to get too upset over it. So the easiest way to evaluate a limit is what method? Direct substitution. So we're going to try direct substitution because it's easy, right? But it doesn't work. Why?
Why didn't we do this before?
We did. We just didn't write it down. We did. I asked you about it. I just didn't write it down. That's always going to be the first thing you try because it is the easiest method. And if it works, great, you're done. All right? Anyway, you end up with a 0 over a 0 whenever you use direct substitution. That means that we have to somehow algebraically manipulate this thing. And what you're going to do is rationalize the numerator. Now, we've never rationalized a numerator before because we haven't had to. We always want to get the radicals out of the denominator, so we rationalize the denominator. Well, now we're going through the same process. We're just going to try and get the radical out of the top and see if things fall out and make nice. All right? How do we get rid of the radical up here if we have a square root minus 3? What do I multiply this thing by in order to get rid of the square root on top? So we start with the square root of x squared plus 8 minus 3 over x plus 1. And we're going to multiply this thing by what? Why did I put plus 3? Remember, in order to, if you have two terms here, a sum or a difference, you multiply by the conjugate pair to get rid of the radical. Do y'all remember ever hearing the word conjugate pair? If you have a plus b times a minus b, then you get a squared minus b squared, right? Square the first, square the last. The square root's going to drop out there. So, we're going to need to FOIL this out. Notice I multiplied the top and the bottom by the same thing because I don't want to change the value of this fraction. And this is equal to 1, isn't it? When you have the same thing on top as you have on bottom, that's equal in value to 1. So all I'm doing is I'm multiplying by 1. That's okay. I can do that. I'm not changing the value of this. I'm going to change the appearance. Okay? So I'm going to manipulate it, hopefully so that the numerator will go, well, it will not have a radical in it. So when I do this, I end up with the first term. Let me rewrite it like this. I have x squared plus 8 minus 3 times the square root of x squared plus 8 plus 3 over x plus 1 times the square root of x squared plus 8 plus 3. When I do this, my numerator becomes what? It's the difference of two squares, right? So I'm going to have the square root of x squared plus 8 squared minus 3 squared all over x plus 1 times, I'm not FOILing out this denominator, I'm just going to leave it alone. Are y'all okay with that?
Yeah. Yes.
Hang on, x squared plus 8 plus 3. So when I square that radical, what does it do? It's x squared plus 8 minus what? See, when you square the radical, square the square root, they cancel each other out, and you're just left with the x squared plus 8 minus what? 3 squared is 9. Sorry, don't mean to ask the hard questions. Over x squared, x plus 1 times that whole thing, x squared plus 8 plus 3. There we go. Now, the numerator will simplify into what? I don't want to write it out again, okay? Can I cheat a little? All right, but the numerator factors into what? X plus 1 times x minus 1 over, now I'm going to write it out, x plus 1 times the square root of x squared plus 8 plus 3. And guess what's going to cancel? So now I'm looking at the limit as x approaches -1 of x minus 1 over the square root of x squared plus 8 plus 3. Now I can use direct substitution, right? Yes. When I plug in a -1, -1 minus 1 is -2 over -1 squared is 1 plus 8 is 9. Square root of 9 is 3 plus 3 is 6. This whole thing is -1/3. Whew. We did it. We evaluated that limit.
I have a question.
Yes.
How did you decide what to multiply?
Experience.
You just looked at it and knew? Or?
Yes. Okay. Here's how I decided. A, it's experience. But B, because I know a strategy for finding limits. Let me give that to you. That might prove helpful. Let me do this. This will answer your question. First of all, identify which limits can be evaluated by using direct substitution. That's what you always want to try first. Direct substitution is the easiest way to evaluate limits. It's hard to talk and spell at the same time. Next, if you cannot use direct substitution, try algebraic manipulation. By algebraic manipulation, what I mean is reduce your fractions or rationalize the radicals. Okay, that's how I knew. Huh?
How do you rationalize radicals?
Multiply by conjugate pairs. Hang on. I'll answer your question. Conjugate pairs are things like A plus B times A minus B. And the reason you do that is this factoring pattern is the difference of two squares when you FOIL it out and you get the first term squared minus the last term squared. That gets rid of your radical. Okay, that's why you want to use the conjugate pairs. Because if I would have just multiplied by the square root, I still would have had that square root with the 3 because I would have distributed. Okay. All right. And then, if all else fails, this is the toughest to get the exact answer, but use a graph or a table. That should be a P, not a B. All right, when we got that answer of 2 square roots of 2 for that limit, you wouldn't have gotten that exact value looking at a graph. The correct answer is 2 square roots of 2. The decimal approximation you could carry out to 12 places, but it's still an approximate value. You always want to get the exact value, unless otherwise specified. Okay?
But if it was like an estimate, couldn't figure out what to do.
Hey, punt. Hope for partial credit. All right. So this is actually the order in which you want to try things. Okay? So I'm going to stop with that today and